So good evening all. So we'll be continuing with the week 10 problem solving section of the engineering hydrology course. So basically in the previous sections, previous week we were dealing with hydrographs. So hydrographs are nothing but the when a precipitation occurs in a catchment or a watershed, the water that falls on the watersheds, the different types of storages all gets filled up, and then we saw how the overland flow starts, and this overland flow or the sheet flow then gets distributed into the and forms a network of channels are called the stream flows. So how we can convert the uh, what we say the precipitation into the runoff that is generated in the catchment. So that process we saw, that is how the precipitation, if we have the precipitation, how it is get converted to runoff. And we saw all the rainfall runoff models, and we saw all the assumptions related to the rainfall runoff models. Like we are considering it as a analogous to a linear system, and whatever we get at the outlet, that is the discharge of the discharge that is coming to the other flow rate of water, volumetric flow of water that is coming at the outlet point versus time. That is something called the hydrograph. That is the temporal variation of runoff at that particular point. So that was we saw in the previous lectures. We were seeing all the types of hydrographs. There are like different what we say there are different uh, tools that are used to derive one particular storm hydrograph, particular storm unit hydrograph, and to another unit hydrograph of another duration of storm. And we saw different hydrographs like S hydrographs, which are generated due to a step input, that is rainfall that is occurring from 0 to 1 at t equal to 0 and remaining 1 indefinitely. So what is the purpose of a S hydrograph, and where we'll be this like an hypothetical case, right? There is nothing like in reality like a rainfall that is becoming 0 to 1 unit or 1 inch or 1 centimeter in the t equal to 0 and remaining indefinitely constant. So that is something a hypothetical case, and how where we will be using such cases, such hydrographs, and what is the purpose of using those hydrographs. That all we saw in the previous lecture. And current in the current lecture, mainly what we'll be focusing on is the what we call the flow routing. So this lecture is a very short lecture. We'll be uh, in the very short lecture which was covered in the week 10. In that we were mainly dealing with something called a flow routing. So when it comes to flow routing, what we saw in the lectures was what is flow routing? Flow routing means we have the one particular hydrograph, that is from the rainfall we already generated a hydrograph for that particular catchment at one particular point. Say we have generated the hydrograph at a particular point in the upstream. So if you want to know what is the flow that will reach in the downstream we have a point, what will be the hydrograph there? Will it be same as the hydrograph we got in the upstream, or is there any differences? What are the differences? How we can derive that? So this process of deriving the hydrograph at a point in the downstream or any point in the catchment, given an in a hydrograph in the upstream, so that particular process is called routing or flow routing. So basically, we are trying to generate the hydrographs at different points, spatial points, different points we are taking, and we are trying to generate the hydrograph of at those points. Okay, so this is the basic idea of flow routing is. And in this lecture, we'll be in the previous week or week 10 lecture, we saw different types of flow routing, that is hydrologic flow routing and hydraulic flow routing. What are the differences that we'll be covering? And mainly in the based on the syllabus, in the lecture we are focused only on the hydrologic routing. And within hydrologic routing, we saw two types of routing, that is reservoir routing and what we say the river channel routing. So these are the main things that are the primary thing is flow routing and our in within flow routing we have been more focused on the hydrologic routing. Hydraulic routing, the theory, what the concept has been brushed upon, but we won't be going into depth. But in hydrologic routing, we will be seeing two cases. That is, one is reservoir routing and a channel routing. Reservoir routing is nothing but there is a inflow coming to a reservoir and the outflow will be generated at the downstream of the reservoir, right? So we have the inflow hydrograph with us. We have to derive the outflow hydrograph. That is called the reservoir routing. And river channel routing is in the river at the upstream point, we have a hydrograph with us. We need to derive the hydrograph for the downstream side. So that is what we have seen. If you have already watched the lectures, that is what ma'am has covered in the week 10 lecture, and we'll be trying to cover like a revision. It would be like a revision for you when we solve the MCQs and we have problems, that is numerical problems to it would be like a practice for you for your exam, and also it will be like a practice for solving questions which are taken from standard textbooks. So before we start the section, I'll give a brief introduction of myself. I am Akhil. I am currently doing my fourth year of my PhD in IIT Delhi. I'm working under the supervision of Professor Denya, and I did my bachelor's BTech from NIT Calicut in civil engineering discipline, and then I did my MTech from an IIT Guwahati in water resources engineering and management under the supervision of Professor Srija Pekat, and currently I'm enrolled for PhD in IIT Delhi from the year 2022. And those who have been following my lecture, the pattern which I follow would be I'll be having few 6 MCQ questions. These MCQ questions are taken in such a way that we can brush up on the theory concepts which are very much important for solving the questions that have been covered in the previous week. And once we are done with the uh, we brush up the concepts and done clear with the how these equations, how these formulas have been derived and has coming up, and then we will be focusing on the numerical answer type questions, which mainly would be like a practice for you to tackle questions in your exams that is coming very shortly, and also to have an understanding better understanding of problem solving. Okay, so we can start with the section. So before we start, the first question, I will give you just brief whatever we discussed now. We will be giving a bit of brief about whatever things we have discussed with. So the main topic we will be focusing today is flow routing. So just to be on track, what is a flow routing? The formal definition is the procedure to determine the time and magnitude. So you already know we are trying to derive hydrographs, right? So we need the time and the hydrograph, that is a flow rate. That is flow hydrograph at a point at the downstream of the river or a reservoir. So we are taking two cases. Either it is at a point in the downstream of the river, we have given with the upstream hydrographs, or we have given the inflow hydrograph of the at the inlet of the reservoirs. We have to find the flow outflow hydrograph at the downstream of the reservoir. Okay, a reservoir from the non hydrographs. So we are given with the upstream hydrographs at one or more points. right? So it is a procedure to determine the time and magnitude of a flow hydrograph. That is, time magnitude means we have to find the flow hydrographs at a given point that can be in the downstream of the river or in the downstream of a reservoir. And we are given with the non-hydrographs at the one or two points in the upstream. That is how what is a that is a mean uh, meaning of what is a flow routing means. So if you take consider a catchment like this, and we have the mainstream and we have the tributaries or substreams, and we basically know the hydrograph here. At this point, we have done all these analysis that or rainfall runoff model. We have modeled it and we got the rainfall hydrograph here. Or we have this particular station is gauged and we know the outflow hydrograph here. So this is the hydrograph at this particular point. This is Q versus time. Okay, so we are taking another point, say towards the outlet, and at this point we are trying to, so this is given. This particular hydrograph is given, or we can say it is a gauge station here. So we have the hydrograph with us. Okay, and next, what we'll be doing at this particular point over here, which is very close to the outlet, if we set up a gauging station at that particular point, we'll be trying to uh, find this particular hydrograph with the help of this hydrograph. Okay, so this will be our Q and this will be our T. So this we need to find unknown. So this process is called the flow routing. Okay, so uh, so with this basics, uh, we can move forward. And also, if you see these two hydrographs, we can see there will be a difference in the peak. So this peak and the peak of the uh, the upstream hydrograph and downstream hydrograph won't be will be different. Also, the slope of the rising limb and slope of the descending limb, that will be also receding limb, that will be also different. And also the time to peak, that is the time taken from for the flow rate to become the maximum flow rate, is also different. So these are the different changes that we can see in the upstream and the downstream hydrograph. So how we can model these changes and how we can come up with the downstream hydrographs given the inflow hydrographs. That is what the flow routing means. So there will be changes, of course, because it cannot be, because we can see here this particular point, the our upstream point. This point, after some time, it has the influence. Water from these tributaries will be contributing, right? So this water from these tributaries will be contributing, and the water in and along the stream, if there are any depression storages, those storages will be met, and whatever that is left, that will be reaching Q, right? So, so in the that so it will be different. Of course, it will be different. There will be difference in the peak and there will be difference in the time to peak. There will be difference in the rising limb slope, whereas the difference in the receding limb slope. So we need to understand how all these are taking place, how and get the outflow hydrograph. Okay, so that is the basic idea of flow routing. And now let's come to the first question. And along with this, we'll move on with the other concepts. The first question is, what is the primary difference between hydrologic routing and hydraulic routing? So there are two things. So we know what is routing is, and now we have been asked two things, that is hydrologic routing and hydraulic routing. What is the difference between these two, hydrologic routing and hydraulic routing? So we already saw what the uh, routing means, and now we can come to the types of routing. So there are two types of routing. So one is hydrologic routing and the other is hydraulic routing, right? So we need to understand the differences here. So in hydrologic routing, what we does is both are methods that are used to find the downstream hydrograph with if given the upstream hydrograph with us. Okay, so both are the different types of routing techniques. So in case of hydraulic routing, it is governed by it is governed by when we are trying to model, we were using the RTT and we are trying to apply the system of equations that are defined in the Lagrangian frame of reference to the Eulerian frame where the fluids can be defined, right? So here also we will be routing with the help of our standard laws of conservation laws. So in case of hydrologic routing, we will be making use of continuity equation or conservation of mass, and the other thing is the flow storage relationship. So based on these two equations, there will be a continuity equation, and in addition to that, there will be a flow storage relationship. With the help of these two equations, we will be trying to model our or trying to model to find the outflow hydrograph. Okay, and in case of hydraulic routing, it is governed by continuity equation and momentum equation. So this is a standard thing, right? Where whenever we were talking about, in the case of, for example, we saw uh, evaporation. There also we were trying to model with the help of RTT. We were using the momentum and the continuity equation, right? So this is a standard well as method which will give you accurate outflow hydrograph with the help of continuity by solving the continuity and momentum equation. That is hydraulic routing. Okay, and the second point is it is a lumped flow routing. That means in the previous lecture we already saw what are the different types of hydrologic models are. We know there are first of all there are deterministic models and stochastic models, right? And within the deterministic models we had lumped model and also distributed models. So the lumped models are the ones in which the spatial heterogeneity or the spatial heterogeneity is not considered. We consider it as a lumped system, that is, the rainfall is falling over the entire catchment, but we tried to model the outflow hydrograph at the point of outlet, right? That is, we are considering it as a lumped system. Here also, we will be considering our system as lumped. The spatial distribution is not taken into consideration. And when we come to a hydraulic routing, since we are using both momentum and continuity equation, we will be calling it as a distributed flow routing. That is, at each and every point, based on your discretization, at each and every point in the catchment, you can get the hydrograph flow. If we have the inflow, we can get the at each and every point. It is like a spatially distributed. The output you will be getting, or the flow rate at each time step across the every points in the uh, catchment can be modeled. So that such routing is called hydraulic routing, and it will be also called as a distributed flow routing. Okay, and finally here third point is, so the variation with respect to time is considered. Variation with respect to time is considered, and in hydraulic routing, the variations with respect to both time and space is considered. So that means in hydraulic routing, the variations with respect to time is considered only time. So that's why it is called a lumped model, right? Lumped unsteady we can call lumped unsteady model and routing model. And in case of hydraulic routing, the variations with respect to both time and space, that is called a distributed unsteady model. Right, so the model is unsteady, that is, it is the variation in with time is considered in case of both hydraulic and hydrologic routing, hydrologic and hydraulic routing, and the variation with respect to space is considered only in hydraulic routing. Understood? So further, so from this, I think it is almost clear what a hydraulic routing and what a hydrologic routing is, and basic idea is clear to you. And now I will give a brief, like we can go back to the question once, and then I will give a brief more details about what is a hydraulic routing is. And in the coming questions, we can go into the details of the hydraulic routing. And after this, I will be giving a short description, a brief description of the hydrologic routing. So, so the first option is hydraulic routing is used for reservoir and hydrologic routing is used for reservoirs, while hydraulic routing is used for channels. No, both are can be used for both the system, right? Hydraulic, both are routing techniques only. Hydrologic routing is uses both continuity and momentum equation, whereas routing uses only the continuity equation. So that is the opposite. That is wrong, right? It is the opposite was true. Hydrologic routing employs a continuity equation only, whereas the hydraulic routing employs both continuity and momentum equation. So this was the correct answer, right? Option C. Option D was hydraulic routing assumes steady uniform flow, whereas hydrologic routing assumes unsteady non-uniform flow. Wrong. So basically, so this is the main difference in hydrologic routing. We can consider the continuity equation along with a storage flow relationship, and in case of hydraulic routing, we consider both the continuity and the momentum equation. So I will give a brief about what is hydraulic routing is. Not hydraulic, no, hydrologic routing is. Okay, so we are dealing with hydraulic routing, sorry, hydrologic routing. Okay, so basically what it does is we have a inflow hydrograph. Say this is our inflow hydrograph. Okay, this is the Q versus T, or if I can call it I versus T. We'll passing it to a to something called a transfer function. We'll be passing it through something called as a transfer function, and we'll be getting an output. QSST, that is the outflow. So this is inflow and this is outflow. So this is the basic idea of a hydraulic routing, hydrologic routing. And here we'll be making use, so I already mentioned, we'll be making use of the continuity equation, right? So we'll be basically making use of the continuity equation, and uh, so in the continuity equation we know it is a unsteady so the continuity equation for unsteady case, unsteady system, unsteady process, we already know that is ds by dt, that is change in storage, is equal to inflow minus outflow. So this is very clear to you. We have been using this multiple times in the previous lectures also. Right. So here only I is known to us, Q and S both are unknown to us. Right. And then we represent S as a function of inflow and its derivatives, so on, and also outflow and its derivatives. This was our storage function, right? So this also we saw in the previous lecture, right? And then so the so basically then depending on the nature of the system, we analyze the storage function in different forms. So based on the nature of the system, so what types of this type of the system we are dealing with, we can define different forms of this particular storage function S. So this is a storage function. It takes different forms depending on the system. So depending on the system, it takes different forms. The first form is when the storage is a function of outflow only. So we know storage has been defined as a function of inflow and its derivatives and outflow and its derivatives. If the storage is being defined as a function of only outflow, then such model is called a first is called a reservoir routing or level pool routing. This is called reservoir routing problem. Reservoir routing we can call it. Okay, so in case of reservoir, the outflow will be a function, the storage will be a function of outflow. Okay, and the second form it takes is when the linear function of storage is a linear or else uh, is linear function of both inflow and outflow. Then the method that will be used, so this method is called flow routing in river channels, and this is what that is being used in this is what that is basis that is used in our Muskingum method. Okay, and in case of reservoir routing, that method we will be using is called level pool routing. It's clear. So what it basically says is that we will be making use of the inflow hydrograph, we will be making use of the continuity equation, and along with the continuity equation, we will be having a flow storage relationship. And if the storage is a function of outflow only, then we will be calling it as a reservoir routing. This particular function will be used for reservoir routing, or it is also called level pool routing. And if the storage is a linear function of both inflow and outflow, not its derivatives, only inflow and outflow, then we will be using this particular condition for river flow routing. And this is the basis for the Muskingum method. So in this particular lecture, the two main things that we will be considering is the reservoir routing and the level pool routing. Clear? Okay. Then, so both the important method, that is the level pool routing and the Muskingum method that we'll be discussing today will is a part of the hydrologic routing or a lumped routing method. Okay, it's not a distributed one in which we are using both the continuity and momentum equation and RTT and all. Okay, and so only then the difference is that in reservoir routing, storage is the function of Q alone, that is the outflow alone, and in Muskingum method, storage is a linear function of inflow and outflow. That should be clear. Okay, so next we can come to the second question, that is the unsteady non-uniform flow in an open channel is mathematically represented by a sign-Venance equation, right? So sign-Venance equation is the basic equation that is used to model unsteady non-uniform flow in an open channel. So if you have taken the courses of related to open channel, this will be very clear to you. And this same sign-Venance equation is the basic for our hydraulic routing also. So these formulation are of which two basic conservation of flows. So the Sen-Venance equation, so I already told you it is the basis for our hydraulic routing. So there we will be using Sen-Venance equation, right? So then this the basic conservation laws will be nothing but the conservation of mass and conservation momentum, right? So I'll give a brief explanation of this, how we can make use of these conservation laws and come up with the what we say, come up with the make use of the conservation laws and come up with the equation for the hydraulic routing. So basically, this would be following the same procedure that we followed for other hydrological processes like evaporation, infiltration. What we did every there was we were using RTT, right? So we are going to discuss about the second type of routing, that is hydraulic routing. So here basically we'll be making use of, you already know, two equations, that is continuity equation and momentum equation. So how we can apply this equation to a fluid system? For the fluid system, you already know we have these conservation laws defined in the Lagrangian frame of reference or the point systems. And if you want to apply it to fluid systems, the better way is to apply it in the Eulerian frame of reference, right? So for that, we use a theorem that is also familiar to you. We have used it multiple times. That is the RTT, or the Reynolds transport theorem. So for for that, we are going to apply the Reynolds transport theorem RTT. So the rate of change of extensive property is equal to rate of change of volume integral of intensive property beta rho dV plus the surface integral of across the control. This is across control volume and this is across control surface, that is the inlet and outlet surface, rho beta V dot dA. So this is our Reynolds transport theorem, right? And now we need to consider a control volume for this derivation. So control volume, if you take a channel like a prismatic channel, if you take, so this is the bed slope of the channel, and say for example this is our datum. So this is our datum from which we do all the measurements, and we take 2 points and we consider this is the water surface elevation. Okay, so if you consider 2 points, 1 point is over here like this, and the other point over here like this, and this is our, this shaded region is our, if we call this as our control volume, this yellow shaded region is our control volume, then it has an inflow Q coming this side, and the outflow from this particular side will be Q plus dou Q. So this direction is X direction. So this particular direction is our X direction. So dou Q by dou X into dx, right? And this length, that is our, this elemental length of our control volume is taken as dx, right? And say this vertical is called the y direction, and this head is the datum head, and followed by a velocity head will be there, that will be equal to v square by 2g. This will be the HGL, that is hydraulic gradient line, right? So these are two sections, 1 and 2. So this is the control volume that we consider, and this will be our datum head is set. Okay, so for this we will be trying to apply this particular Reynolds transport theorem, that is the rate of change of extensive property has the rate of change of the intensive property across the control volume and the controls and across the control surface, right? So this, when we, so now let's come to the continuity equation. Here how we will be applying the continuity equation is that we consider our extensive property as mass. So dB by dt will be becoming 0, and beta is equal to dou B by dou M, that will be equal to 1. So this you already know. So we can write it as 0 is equal to d by dt across the control volume rho dV plus across the control surface rho V dA. Okay, so this is the expression we'll be getting for conservation continuity equation, right? Then when we further substitute these values for the control volume, if we consider as prismatic, then the dV can be equal to dA into height, right? So if you do those simplifications, finally we'll be getting the continuity equation has something. So the derivation ma'am has given the detailed derivation in the lecture. You can see that. So after derivation, we'll be getting the final continuity equation as dou A by dou T plus dou Q by dou X minus Q equal to 0, where Q is the lateral inflow happening. So if we have water that is, so it is not mentioned in this particular figure, but if we have water coming from the lateral boundaries, that is through tributaries, that can be considered through in Q. So this is our final continuity equation. And if and the final, similarly, if we try to model the momentum equation, so momentum equation also, the derivation I'm not showing here, the final expression we'll be getting it as, so the unsteady flow momentum equation for unit width of flow, we'll be getting the final expression. If we solve using the RTT, we'll be getting it as dou V by dou T plus V dou V by dou X plus G dou Y by dou X is equal to G into SF, that is friction slope minus bed slope. So this is our momentum equation. Okay, so this momentum equation plus the continuity equation, these two together, these two equations together, we call it the Saint Venant equation. Okay, and within this Saint Venant momentum equation, we will be doing simplification, like if we'll be taking, we'll be considering the friction slope is same as the bed slope, and if we say the if we consider it as a steady uniform flow, then the equation will be reducing to only this much, that is G into SF minus S not equal to 0, that is for steady uniform flow. So steady uniform flow, all the derivatives becomes with respect to time and dist x space becomes equal to 0, right? And we'll be, for steady non-uniform flow, we'll be getting a expression like this. dV by dt will be becoming equal to 0, and rest we'll be getting for steady non-uniform flow. Non-uniform means the flow depth will be changing with space, and the entire expression we'll be getting, and that is for unsteady non-uniform flow. So this equation is also known as kinematic wave equation or shallow wave equation. This is called diffusive wave equation, and this is called dynamic diffusive wave equation. So based on the simplification on the momentum equation, we can classify it in the kinematic wave equation, and uh, diffusive wave equation and dynamic diffusive wave equation. Okay, so this is the basic idea of hydraulic routing, that is solving these two uh, momentum and continuity equation with the Saint-Venant's equation, that is both are differential equation. If we solve this, we'll be getting the flow depth and velocity with a different time, right? So that is the main idea of hydraulic routing. Okay, so coming back to the question, so Sennen's equation, it is the basically it has comprised of two conservation laws, that is the law of conservation of mass and conservation of momentum. So option B is the correct answer. Just all are wrong. Okay, so we can move on to the third question, that is when a inflow hydrograph is routed through a reservoir with a freely operating spillway. So we have an inflow flood hydrograph. That is some inflow happening, some rainfall has happened, and that flood hydrograph is inflow is happening coming to the steady reservoir. And it is routed through a reservoir through a freely operating spillway. That is an uncontrolled spillway. We are not controlling, it is freely operating spillway. So spillway is a structure in the reservoir which allows water to flow to the downstream. So some spillways will be controlled, that even though the water comes in, we will be controlling how much amount of water has to be uh, uh, given out to the downstream. Or there are a freely operating spillway, that is there will be a particular height of the opening. Whenever the water becomes higher than that particular opening, the water will be spilled out. That is called freely operating spillway. It is an uncontrolled one. At what point does the outflow hydrograph reach the maximum peak? So they are asking at what particular point the outflow hydrograph reaches the maximum peak. So here we need to understand something related to the reservoir routing. Okay, so we are discussing something about the reservoir routing. Okay, so basically, when a flood wave that travels to a reservoir, a flood wave travels through a reservoir, two things happens. Water level changes with time, and the storage and outflow also changes with time. So water level or H changes with time. That is when flood water comes in, the level of water in the hydrograph or the reservoir changes, right? So as the water level changes, the storage changes. When the storage changes, that is obvious. And we know in reservoir routing, storage is a function of Q. So storage will change, obviously the Q will also change. So thus Q and S will change. So this is that you already know. So we have a inflow hydrograph or the flood hydrograph coming. We have our system. Now it is not a catchment, it is a reservoir system. And within this reservoir system, we know Q is a function of H, right? Q is a function of uh, H, and S is also a function of. So we can say in this way, in a reservoir, storage is a function of H, right? And this is obviously clear. And for a reservoir system, we also know storage is a function of Q. So from this we can say Q, from this we can say Q is a function of H, right? So these two are important. Both the storage and flow rate is a function of the head, water head, or the water level in the reservoir, and it will produce QT, that is the outflow hydrograph, ST, storage change with respect to time, and HT, these three will be changing. This is the basic representation of a reservoir system. The relationship between S and Q is important has an important influence of flow routing. So S and Q relation. So how S is related to Q? We know S is a function of Q, right? In case of a reservoir system. So this relation is very much important for flow routing, for reservoir routing. Very important for reservoir routing, this particular expression. Okay, so this particular relationship may be, so now we coming to this particular relationship, that is S is equal to F of Q, can be of two types. This relationship can be one, that is invariable storage function, and two is variable storage function. Clear? So this particular relation, that is the storage has a function of Q. This function can be a invariable storage function and linear storage function. Now we need to understand what is an invariable storage function and what is a variable storage function. Okay, so now we can see what is a invariable. We'll be discussing what is a invariable storage function. So in case of an invariable storage function, we have this particular S is equal to F of Q, right? And this applies to reservoir with a horizontal water surface. Reservoir with horizontal water surface, and reservoir pool is wide and deep compared to its length in the direction of flow. Wide and deep pool compared to length, compared to length in direction of flow. Then the velocity of the reservoir is very low, low velocity, and requires fixed discharge from the reservoir for a given water surface. A fixed discharge for given water surface. So these are the properties of a invariable storage function, right? And so here, for this case, if you consider S is equal to FQ, and in the question it is asked, that is the outflow hydrograph becomes maximum. When does the outflow hydrograph becomes maximum, right? So we have our continuity equation, ds by dt is equal to inflow minus outflow. So when the ds by dt, if s is equal to s, if ds by dt when s is a function of s, if ds by dt will be representing the second derivative of that particular function, right? So ds first derivative, so that should be equal to 0 when we have maximum storage. So maximum storage will be when ds by dt is equal to 0. That implies inflow is equal to outflow. This is the condition for maximum storage based on the continuity equation. ds by dt, the derivative of storage must be equal to 0. For such reservoirs, the peak outflow occurs when the outflow hydrograph intersects with the inflow hydrograph. So what does this mean? The maximum storage will be maximum storage or peak outflow will occur when the inflow and outflow hydrograph meet. That is, here the relation S is equal to FQ is a single valued increasing function. That is, when the storage increases, outflow increases. For such case, the maximum storage will occur when Q is maximum. Q is maximum, that is maximum storage or the peak outflow will occur when the inflow will intersect the outflow, right? So if we draw the graph, so if this is the inflow hydrograph and this will be our outflow hydrograph. So here the peak outflow will occur when I will be equal to Q, or maximum storage point. So this is the case for, and if you look at the relationship of storage with Q and storage, it will be increasing like this, right? So we have the maximum storage Q max, we have S max, right? So this is the case for a invariable storage function. So here, when it is an uncontrolled structure, will be it is similar to a invariable storage function. So in such cases, the uh, in such cases, the exact moment in which the flow hydrograph begins to such cases, the outflow hydrograph will be reaching maximum. So we know the answer, it will be outflow hydrograph will be maximum at the point when the storage is maximum, or at the point where the inflow hydrograph intersects with the outflow hydrograph, right? So the options are the exact moment in the inflow hydrograph begin to recede, that is wrong. When the outflow rate is the half of the peak inflow rate, wrong. At the point of intersection where the inflow hydrograph equals to the outflow discharge, that is the correct answer. And final point is the exactly at the time of consideration of the watershed, wrong. So basically what we need to understand in this question is that it is said that the reservoir operation is used through a freely operating spillway that is uncontrolled. So here it will act as a invariable storage function, that is, as the storage increases, the outflow will increase, right? So the spillway has a particular point, more and more water gets stored, more and more water get, the outflow rate will increase, and finally it will become maximum. That is, the opening area will be constant, right? So maximum a particular discharge can be so this will become flat. This particular curve Q versus S becomes flat. Further, if we increase the storage, the flow rate will be constant. So at the point of maximum storage, so we'll be, so that we can find from by differentiating our continuity equation. That means at the maximum, the influx point, ds by dt should be equal to 0. So at the point, another one thing before that, what we need to understand is that ds by the maximum storage point will be same as the storage point, where we will be the same as the time at which we will be having the maximum peak or peak discharge. So ds by dt will be equating it to 0, then we will be getting inflow equal to outflow. So that will be happening when these both are equal. And if you take a variable storage function, In such cases, the peak outflow occurs later than the time when the inflow and outflow hydrographs meet. So there will be a delay. It's not at the point where these both will be meeting. This is because of the retarding effect of the backwater. For example, while we were discussing the invariable storage functions, we said that the reservoir surface should be flat. Instead, if we have a retarding or the backwater effect, the water that is hitting the reservoir walls and it is a backwater is flow or the waves are created. In such cases, we will be calling it as a variable storage. The storage elevation is changing with time. Changing with the influence of this backwater. So there the peak will be formed, the outflow peak will be getting after some time of after the intersection of the inflow and the outflow hydrograph. For such cases, if you draw, you will be getting something of this form. So this is our inflow hydrograph, and the outflow hydrograph peak will be occurring after some time. There is a time, so this is the peak and this is the point of maximum storage. This is peak, outflow, this is the point of maximum storage. Okay, so I hope that would be clear. So that is the end of this question and we can move on to the fourth question. So in level pool routing equation, so we are coming to the level pool routing. So level pool routing, we already know two things, that is the method of reservoir routing, and also we consider the storage as a function of outflow. So we use in particular equation. This is the equation they have mentioned. What does the RHS term S2 into dq2 by delta T by 2 fundamentally help to determine the, how does it help to determine the next time step? So this is basically a question pertaining to the level pool routing method. Okay, so I will give a brief about how we will be making use of this particular method, and then with there is a question dedicated for this. From through that question it will be very much clear to you. Okay, so we are discussing about level pool routing, right? So the fundamental is that the storage is a function of Q. This is the storage function that we'll be using, and we'll be using the continuity equation, right? So based on these two equations, that is, it is a method, hydraulic routing method. So this is basically not a hydraulic, hydrologic routing method, right? So for this we have to use a continuity equation, and in addition to that we should have a flow discharge relation. So we have this flow discharge relation with us, and also we have the continuity equation ds by dt is equal to inflow minus outflow. Okay, then uh, if you try to integrate this, that is integral sj to sj plus 1, the time step, ds is equal to integral j delta t j plus 1 delta t, that is the time uh, intervals 18 dt minus q of t dt j delta t to t equal to j plus 1 delta t, right? So this is the continuity equation. This is the continuity equation when we integrate, and then what we will do is that we will say delta t is very small, so that the variation within the delta t we can consider it to be linear. Okay, so once we say the variations are linear, for example, for jth time step we have storage sj, inflow ij, and outflow qj, and j plus 1 the time step we have storage jsj plus 1, ij plus 1, and qj plus 1 are the storages, are the other j plus 1 times of storage, inflow, and outflow. Then this particular integral we can write in the discrete form, that is s j plus 1 minus s j is equal to this integration. We can do it like sj plus ij plus 1 by 2 into delta t plus qj plus qj plus 1 by 2 into delta t. So here the thing that we are assuming is that we are considering the delta t to be so small such that the variation within the interval is linear. Okay, so then we have this particular equation. Now in this equation we know ij, and we know ij plus 1, right? Also we know qj, that is initial time step or the just previous time step, what is the outflow happening. So that is also known to us, and sj, that is storage at current storage, these are the known terms, and the unknown terms are I is known, sorry, the unknown terms are q j plus 1, s j plus 1. So these are the unknown terms here, right? So these are unknown terms. So then what we do is we try to bring in the known terms together. So we have ij plus I j plus 1 by 2 into delta t plus sj minus qj by 2 into delta t is equal to sj plus 1 plus qj plus 1 into delta t by 2. So these are known terms, and this is unknown term. Okay, this is also called indicative storage, right? So this is also called unnecessary storage. So what we do here is that if we could plot this particular thing, this unknown s plus q by 2 delta t versus the h. So if we could find the value for of a relation of this with h. So we have for different h, we have, so for different h we have q with us and also s with us. So we can substitute those values and find a relation of this indicative storage with h. So once we try to get this unknown term, we substitute all this value in the LHS, we get the unknown term. Then what we will do, we'll put that in this particular relation, that is SQ indicative storage versus H relationship, and we'll be getting that particular H value, and then we'll be using Q as a function of H, right? So from this particular relation we'll substitute that H and we'll be getting our Q. That is the outflow hydrograph. So basically what we'll be doing, if we substitute all the non-values, if we substitute in this particular equation, we'll be getting this RHS. Once we get this RHS, we put this RHS in the S plus Q by 2 delta T plus S H plot that we have already created, because we know the storage and Q functions. Storage, how it is related to Q. And then we find the H corresponding to this particular value that we got, and then we put it to the Q equal to F of H relation, and then find the Q value, that is the outflow of the. That is the main idea of the level pool routing. Okay, so we can come back to the question. It is plotted against the outflow to find the new outflow Q2. So that is the right answer, right? So basically this RHS is plotted against Q, right? It is plotted against Q, and or we can say indirectly we can say it's plotted against X or H, or or and H we get, and yet H will be relating it to Q, or else we can directly relate this with Q also. It can be plotted with respect to Q. Instead of plotting with respect to H, we can directly plot this with respect to Q, right? This also can be done. So if you plot this with respect to Q, for each of this value that unknown value that we derive using this non value, we can get the Q value also. That is the outflow at the next time step. So that is the right answer. Remaining are wrong. That is a basic idea of level pool routing. Okay, so we got our continuity equation. We are making some assumptions. We know the storage is a function of Q, and then we have this relationship. Then what we do with the unknown term, we will be plotting against it Q, and from that we will be getting the Q for Qj plus 1. That is Q for the next time step. Okay, so we can move on to the next question. That is, in a river routing, the total channel storage during the advanced flood wave is composed of two parts. What are they? So, so coming to hydrologic river routing. So we are discussing about hydrologic river routing and flood total channel storage in the advanced flood wave is composed of two parts. What are they? So we can take an example of two cases. Three cases. Case 1, when inflow mm, so case 1, that is when a flood flood wave flood wave reaches the inlet or the inflow region, then before flood we will be having this. So consider as a prismatic channel. So we have this is our base, and this is our inflow, and this is our outflow. So this will be this particular, since it's a prismatic channel, we'll calling this particular storage as a prism storage. And when the uh, flood reaches the inlet, that is a rising flood is coming, then what we'll be getting is something of this sort, and we have a storage like this. So this is nothing but our prism storage that we already marked in the case before flood, and this storage we'll be getting calling it as a wedge storage, and this rising flood we call it as a positive wedge. So this is the wedge storage, and this rising limb we call it as a positive wedge. And the other case, that is case 2, that is when a flood wave is receding. So when a flood wave is receding, so before flood, before receding, so receding, so here it would be like we have our prism storage with us, and the wedge will be called a negative wedge. So this is our negative wedge. This is called wedge storage, and it's called a negative wedge, and this is our prism storage. And so this here, this is the inflow and this is the outflow, right? And when after flood, when the receding wave is gone, then it comes back to the initial state. That is, we have only the prism storage. So this will be having only the prism storage. Okay, so this is the basics of the hydraulic river routing, where we'll be having we are considering two cases when the flood is approaching, that is the rising flood. There we have a positive wedge and a prism storage, and when the flood is receding, we have a negative wedge and a prism storage. This is how we consider the case of river flow routing. So coming to the question, the two parts are now clear to us. That is, one is the prism storage and other is the wedge storage. Wedge storage can be positive and negative. That is based on whether the flood is approaching or flood is receding. So that is clear. Now we can come to the sixth question. So in Muskingum routing equation. So we are coming to the we saw level pool routing. We are coming back to the Muskingum routing equation. So that is a type of river flow routing that we just show. We are considering two storages, wet storage and the prism storage. What does the dimensional parameter x represent, and what is typically its ranges? So we have to come up with the Muskingum equation for this. So we already saw there is two types of storage from the previous question. That is, one is a wet storage and other is a prism storage. So, so this prism storage, we know that the surface is flat. So it is similar to, it can be routed similar to a reservoir storage. Can be considered similar to a reservoir storage. F is a function of Q. Whereas the wet storage, it is a function of inflow. So the Prism storage is a function of Q and the wet storage is a function of inflow. So basically the storage with these two things, we can say here the storage function, the storage is a function of Q and H, Q and inflow and outflow. So this is what we saw in case of a river routing, right? So we are saying storage as a function of both inflow and outflow. And if we consider these are has a linear function, then there is a general expression for total storage. So total storage is given by S is equal to B by A x into I raised to m by n plus 1 minus x into q raised to m by n. So this is the general equation for the total storage which have been developed based on this prism storage and wet storage concept. So in this, x here is the coefficient corresponding to inflow, coefficient corresponding inflow and outflow, right? And a and n coefficient corresponding to stage discharge characteristics of the channel, coefficient corresponding to stage discharge characteristic, and m and the denominators a and m, a and n, and the b and m are the coefficients that represent the average stage volume characteristics. These are also coefficients that represent average stage and volume characteristics. So coming to the Muskingum method, so this is the general expression that we got, right? Now we'll coming to the Muskingum method. So Muskingum method. So here the assumptions are, this is gives the name of a basin. So there they did a lot of tests and they come up with this relation m by n, they are taking it as 1, and b by a ratio they are taking it as k. So the storage function they have derived is coming out to be capital K into x into I, right? X into I plus 1 minus x into Q. And here in this case, we could say this KQ is the volume of prism storage, and Kx into I minus Q, Kx into I minus Q, that is the volume of wedge storage. Okay, so the inflow coming to the wedge is I minus Q, and inflow coming to the prism storage is Q. So based on that, if you multiply K with Q, it gives the prism volume, and if you multiply this with Kx, we will be getting the wedge volume. So this is the basic understanding, and we have derived the uh, relation for this particular storage function. So now what we do, we repeat the same thing. So next, how we are trying to route this is we know S1, we know, so like we have this particular equation that we have already derived, right? S2 minus S1 is equal to, we consider linear delta x to be very small and linear variation within the delta x limit. So our continuity equation, integral continuity equation can be uh, discretized in this format, 2 by 2 into delta t. So this is the format, and S1 and S2 we can substitute here and we can find x1 is k into I x1 plus 1 minus x q1, and S2 will be k x I2 plus 1 minus x into q2. So we can substitute this in this particular equation, and finally we'll be getting our outflow discharge q is equal to C1 a constant into I2 plus C2 constant into I1 and C3 constant into Q1. So this is the relation, this is the called the Muskingum equation, the flow routing, that is Q, that is the outflow in the next time step is given by C1 into Q1, I2, C2 into I1 and C3 into I. So this can be derived, and the equations are C1 is equal to delta T minus 2 kx divided by 2k into 1 minus x plus delta T. C2 is delta T plus 2kx by 2k 1 minus x plus delta T, and C3 is 2k 1 minus x minus delta t divided by 2k 1 minus x plus delta t. So these are the values for the constant, and if we have these two we can route the model. And also there is a relation that C1 plus C2 plus C3 equal to 0. So if you find C1 and C2, C3 you don't have to repeat all the calculation, we can subtract it from 1. C1 minus, sorry, it is 1, sum is not 0, it is 1. So if we calculate C1 and C2, C3 can be calculated as 1 minus C1 plus C2. Okay, fine. So this is how the Muskingum method is built. So these both are the Muskingum and the level pool routing, both are a type of what we say a hydrologic routing method, where we have a storage function and also we make use of the continuity equation. So now we can move on to the numerical answer type question. So have designed two questions. One is dedicated to the reservoir routing. The other will be dedicated to the Muskingum method. So with that, we'll be ending today's section. So a detention reservoir with a vertical side has a constant water surface of 1 acre. So there is a reservoir, detention reservoir, and it's a constant water surface, and it has a surface area of 1 acre, and drains through a circular outlet. It drains through a circular outlet pipe. The reservoir is initially empty, so initial storage is equal to 0. The inflow storage at a 10-minute interval is given. So inflow hydrograph at 10-minute interval is given. So the inflow hydrograph is given here. Okay. So basically 0, 10, 20, 30, and 40. The head water discharge relationship is also given below. So how the head and discharge. So as the head increases, discharge is increasing, right? So that is also given. Now we need to use the level pool routing method to calculate the reservoir outflow and also calculate whether there is an attenuation. What is attenuation and lag? So attenuation means the difference in the peak of the inflow and outflow hydrograph, and lag is after the peak occurs of inflow, how much time it takes the outflow peak to occur. That is the lag. Okay. So basically we have given with the water. So what the very first thing what we need to do, so I'll be making use of the same table. I'll be extending these tables and solving. So we are given with the outflow water uh, head and outflow. Otherwise I can make another table that would be better. So we have water. It would be better if I use the same table. I'll use a different color, but so water depth we need to find the storage first, right? Storage S in feet cube we can find cubic feet, right? So how can we find the storage? We are given with the head. Okay, so we know our area, surface area. So the area is surface area of the reservoir is 1 acre, that is 43,560 feet square. 43,560 feet square is the area. So storage will be area into head. So this would be storage, right? So for this equation we'll be using. So we have the storage, we have the area. If we multiply with the head, that is water table depth, we'll be getting the storage. For 0, initially the storage is 0, the water table head is also 0, and for 1, the storage will be 43,560 into 1, that is 43,560 cubic feet. For 2, it will be 2 into 43,560, that will be 87,120 feet, and 3 into 43,550, it will be 1 3 uh, that will be around 1 3 130,680 feet cube, and 4 into 43,560 will be 174240. So this is the storage that we got. Now what we need to do, so I already saw, we need to plot store one particular function with q, right? So we have the q with us. For each q we need to plot something called this particular s plus q by 2 delta t, that we already saw. This unknown term relationship with we need to find with q. So we have s with us, we have q with us, so we can find 2s by delta t plus q. So this we can find in cubic CFS, right? So here delta t, so here for this delta t is equal to, I think delta t time is 10 minutes, right? So 10 by 60. So 10 minutes, no, by not by 60. So if you have to convert in seconds, 10 into 60, that is 600 seconds. So this will be 2 into 0 plus delta t into 0. So this will be 0. 2 into 435 is 0 divided by 600 plus delta t. So one solu calculation will be showing this 43560 into 2 divided by 600 plus q, that is 10, that will be around 155.2 CFS. And similarly 87120 into 2 by 600 plus 25, that will be 315.4. And if similarly if you find this, it will be 480.6. and this will be 650.8. So these are the values of the 2s by delta t plus q for different q and s values. So this we already found out. This we will be using later. Okay, so now, so this equation we already know, right? So this equation, if you multiply this throughout by 2, this particular equation, if I multiply it throughout by 2, what I'll be getting is I j plus I j plus 1. This plus 2sj by delta t minus qj is equal to 2sj plus 1 plus sorry 2j plus 1 by delta t plus qj plus 1. So this is why, so we had made this particular column was 2s by delta t plus q. Okay, so this is the unknown term, so that's why we made this relationship phi by q, so that we can find this unknown. This unknown can be calculated using these non terms, and then we have this particular relationship already with us, and from this we can find the q values corresponding to this unknown 2j plus 1 delta t. Okay, so I'll be making a new column here for the routing problem. So we have our j, or we have j starting from 1, 2, 3, 4, 5, 6, 7, and so on. We have our time in minutes, that is 0, 10, 20, 30, 40, 50, 60, 70, like that. And we have inflow I 0, 80, 160, 120, and 0. And we can calculate I j plus I j plus 1. That will be here. I can write it here. Here's 80. 80 plus 160, that will be 240. Then this would be 280. This will be 120. Remaining will be zeros. So that is one, this particular term. And we have the next term has 2sj by delta t minus qj. So that for the initial time step, sj is equal to qj is 0, so that will be 0. And here we have the unknown 2sj plus 1 by delta t plus qj plus 1. Okay, so here initially we'll be don't having any value because sj plus we have not calculated yet, uh, and the final q will be 0 because initial outflow is 0. Then next what we'll be doing is, we know this particular unknown column, that is sj plus 1 by delta t is equal to ij plus 1 ij plus ij plus 1. So we can add these two. If I put arrow, if we can add these two, we'll be getting the value here, right? So this particular time step. So thus that will be 80 plus 0, that will be equal to 80. right? So once we get 80, we need to get Q from this 80. How can we get this Q from? So we need to get uh, Q from this 80. So we already have a relationship here, how Qs by delta T is related to Q. If our Qs delta T plus Q is equal to 80, it lies between the first two terms, that is 0 and 1500, right? So the outflow will be between 0 and 10. So what we do a linear interpolation, and then we take up the value where 80 is equal to where 2s plus delta t plus q is equal to 80. So here I can do show you the sample calculation. So we know we have 2s 2s by delta t plus q is equal to 80. So we need to derive what is our q from this. Okay, so q lies when this lies between 0 to 155.2. Q lies between 0 to 10. So if you do a linear interpolation, then the y will be equal to y2 minus y1 into x minus x2 divided by x2 minus x1. This is the formula for linear interpolation, right? So here our y will be, y is nothing but s by delta, y is nothing but our q. So q will, this will be y1 plus, sorry, y1 plus this particular value. So y1 is nothing but q1, that is equal to 0, plus y2 is 1, 10 minus y1 is 0 into x, we'll keep it as for what we need, that is 80, minus x1, sorry, x minus x1 is nothing but uh, 0 divided by 155.2 minus 0. So if you solve this, we will be getting our uh, q value to be 5.15 CFS. So this is how we get our q corresponding to 80 2s by delta t plus q. So we can write it here as q is equal to 5.15. So next, what we do, if we have, if this particular expression, if we subtract 2 times qj plus from this, then we'll be getting this particular thing, right? If 2j is qj is, sorry, qj is subtracted from this particular time step, or j plus 1 in from this particular time step, we'll be getting the previous column value, right? So if I subtract 80 minus 2 into 5.15, I'll be getting this particular column, that is equal to sj by delta t minus qj. So I'll be doing that subtraction and I'll be getting this particular value. So that will be around, if I do this subtraction, it will be coming around 69.7. So I can write those value here, 69.7. So one cycle is complete now. So the next cycle is, we will be going like this. We will be adding these two to get this. So 240 plus 69.7 is, it will be around 309.7. Corresponding to 309.7, we will be doing the interpolation here. Same way, 309.7 will be lying between these two values. That is, our discharge will be some value between 10 and 25. If you do that, we'll be getting the after interpolation, we'll be getting our discharge has 24.466. So once we get this discharge, then what will we do? We double it and subtract it from since 309.7, right? Then we'll be getting this particular value that will be around 260.77. So once we have 260.77, then we add these two, then we will be getting this particular column that will be equal to 540.77, and we will be interpolating and we will be getting this particular discharge value corresponding 540.7, that is 53.84. Then again we double it and subtract it from 540.77 to get this particular value has 433.09. Then we add 120 to it to get this particular column as 533.09, and from the table from the earlier table we interpolate and get our discharge as 55.648. Then again we double this and subtract it from here. We'll be getting this as 441.79. Then we add with the inflow has become 0, so it will be 441.79 here. We'll be getting the discharge value is 40.302. We double it and subtract it from here. We'll be getting it as 361.19. Inflow is 0, so here also it will be 360.19. From by interpolation, we'll be getting the outflow discharge as 30.543. We double it and again subtract it, we'll be getting it as 300.10. And once we get 300, inflow is 0, so inflow plus this value here will be also 300.10. And if you interpolate and find from the graph, it will be 23.57. So this is our inflow hydrograph and our routing is complete now. I'm stopping our routing here. We can further do it further, the discharge will be decreasing. And if you we can observe the peaks, so the peak inflow occurs at 280 at time equal to 30. No, sorry, the peak inflow occurs at 160, I equal to 160 at t equal to 20 minutes, and peak outflow occurs as 55.648 at t equal to 40 minutes. So from that, the lag time is nothing but 40 minus 20, that is equal to 20 minutes, and the attenuation is equal to, we have our attenuation that is 160 minus 55.648, that will be coming around 104.35 CFS. Okay, so this is how we route the outflow hydrograph with the help outflow hydrograph, that is a flood wave coming to the reservoir which is initially empty, and how we out the outflow hydrograph. Okay, so I hope this is clear. Uh, Now we can go to the next question of the Muskingum method of flow routing. So with this is the last questions, then this will be closing this section. So, so we can start with the uh, Muskingum method. So we have an inflow hydrograph to a river reach in a column that is given in the column 192 of table below. So this is the inflow hydrograph for different time interval, and the delta t is 1 hour, and k and x values are given. So the there was a question, so we didn't come back to the question, I think. So there was a question. Okay, we didn't come back to the question. So in this question, they were asking the Muskingum equation. What does the dimensionless parameter x that typically, what is its typical range? Okay, so we had derived the expression for the Muskingum method, and the x was uh, the question was what was x and what is the waiting factor. It represents the travel time and ranges from 1 to 5 days. It represents the storage waiting factor and ranges from 0 to zero point 0.5. It represents the prism storage volume ranging from zero point 0.5 to 1. It represents the channel stop ranging from 0. So the K basically represents the storage, the wet storage waiting factor that is between 0 to zero point 0.5. The range is between 0 to zero point 0.5. So this is the answer. Okay. So if I go to come back to this particular question, so this is the answer. So with the wet storage, the prism storage was K into Q, right? And the wet storage was K into X into I minus Q, I minus Q. So this is was how we define the prism and wet storage. So it is the weighting factor for the wet storage. Okay. Now we can come back to the Muskingum method. So these are the routing period and inflow hydrographs given. So the very first step, we need to find the C1, C2 and C3, that is the constant. So equation we have already mentioned here. So these are the equations to be used, C1, C2 for C1, C2 and C3. So we can directly, I'm directly substituting those equations. So C1 will be 1 minus delta T minus 2 into K 2.3 into X 0.15 divided by 2 into 2.3 into 1 minus 0.15 plus 1, that will be equal to 0.31 by 4.91, that will be equal to 0.0631, and C2 will be 1 plus 2 into K, that is 2.3 into X, that is 0.15 divided by 2 into the denominator is same, so we don't have to repeat it. It is 4.191, that will be equal to 1.69 by 4.91, that will be around 0.43442, and C3 will be, we can find it by 1 minus 0.063 plus 0.3442, that will be around 0.5927. So we got C1, C2 and C3 with us. Now we have our formula. Q2 has C1I2 plus C2I1 plus C3Q1. So this is the formula for routing. Okay, so I will do one thing. This move it. This I will move it aside so that I can do the calculations here itself. So next we will be having inflow. We have this will be C1 ij plus 1 here, C2 ij here, C3 qj here, finally outflow q here. So this is pretty much straightforward, right? So C1 ij plus 1 means it will be in the j plus 1. So the next time step, that is 93 into C1. C1 is 0.0631. So 93 into 0.0631, that will be equal to 8.6. And C2 will be, C2 we have 0.3442 into I 137, that is equal to 32. And C3 into Q naught. Initially the initial outflow is given in the question, so it is 85. So C3 into 85 will be equal to 50.4, and if we add all this we'll be getting 91, right? Again the same step, C1 into ij plus 1 is 137, that will be 13.1, this will be 47.2, and we have 91 as our Q. So C3 into 91 is 54.0, that will be 114. Similarly, we'll be getting for this as 20.2 and 71.6, 67.7 and 159. Then t equal to 5, we have 27.9, and this will be 110.1. This is 94.5. This is 233. So you can do the remaining calculation. It is pretty much straightforward. The only part is finding C1, C2, C3, then seeing up according to the uh, J values. We have to substitute this. So here this is C1 into J, C1 is ij plus 1 means C1, that is C1 into 137 the first time step, C2 into J means C2 into 93, and C3 into Q means C3 into 85. So if you have to just have to uh, continue this, so I will just write on the other answers. So 240, this is 34.5, then 39.8, this 42.8, this will be 43.6, this will be 42.6, this will be 40.0, then 36, then 30.1, then 24.6, then 20.8, then 15.6, becomes 11.6, 8.5, 6.8, finally 5.7. C2J, uh, it will be one after 110 to 152.1, 187.9, 216.8, 233.4, 237.8, 232.3, 218.2, 196.5, 164.2, 134.2, 113.2, 85.0, 63.3, 46.1, and finally 37.2. And C3Q2, this will be 1 multiplied by the previous Q. After 94, it is 137.8, 192.3, 248.9, 301.4, 342.8, 369.4, 380.4, 337.1, 357.3, 323.6, 283.7, 244.5, 202.2, 162.4, and 127.6. Next, we just have to add all the three terms to get Q. 233, next with 324, 420, then 509, 578, 623 and 642, then 635, 603, 546, 479, 413, 341, 274, 215, and finally 170. So this is the routed hydrograph at the outlet or the uh, outlet point or the outflow point. And now if we want to calculate the lag and attenuation, so we have the peak inflow has 691 at I ninth hour, and we have peak inflow it has outflow as 642, and it is coming in the ninth it is coming in the 11th hour, 11th hour. Okay, so it is coming in the 11th hour. Okay, so our lag is equal to 11 minus 9, that is equal to 2 hours, and attenuation, sorry, attenuation is equal to 642 minus 691, sorry, 691 minus 642, that will be around 49 CFS. Right, so this is how we route the equation. So we need to have an understanding of the equation. We need to find C1, C2, C3, and based on the IJ locations, we have to just substitute and get the outflow. So with this, I'm stopping this section. So if we have any doubt in the today's problem solving section, or if any doubt in the assignments or anything, you can contact me. My will give my details. My name is Akil J, and my email ID is akilnyanadevan at gmail.com. So thank you for attending today's section and closing now.